G'day everyone, we're back today. Today's Monday, so we're starting a new topic. We're in chapter 6 in our book, but it's not about the chapter in the book, it's really about the syllabus points. And the first couple of syllabus points, 3.1.1 through to 3.1.4, deal with exponential functions. Now last year we did a little bit of work in exponential functions, so hopefully you're remembering what they are. Let's just do a quick recap. This is really an exponential function. Okay? Because it has what we call an exponent or a power. Most people would just say the power of, but it's technically called the exponent, and this is your base number. Now if we look at these three that I've got here, 2 to the x, 3 to the x, 4 to the x, they're all of the same family, they're all of the same variety, and you can see the diagrams here, I've colour-coded them to match. So as the base number increases, the steepness of them increases. But you'll notice in this case, they all go through the same point right there. And that makes sense because if I put 0 into all of these, they would all be a number raised to 0. And whenever we raise something to the power of 0, the answer is 1. So that point right in there is going to be the point 0, 1 for all of them and any of them in this family. If we add a number on the end or we add a number in the exponent, things change a little bit. But in this family, the standard family, whenever we cross through the y-axis, it will be at the point 0, 1. Okay? But what about this guy? We did a bit of work with him last year, e to the x. E is just a special number. Okay? The idea of a kind of special number is there's some things that happen with e to the x that don't happen with the other ones. This number is actually 2.71828, I can't remember after that. It goes on forever. It's a bit like pi. Now the reason that this one is special, 2.718, it'd fit kind of between these two. I'll just draw it in. Actually, I might get rid of the green one here. Okay. And I'm going to draw in this one now in green. Because it's 2.7, it's going to fit somewhere between there. So I'm going to cheat a little bit. I'm going to draw that part and then that part there. So this is now my diagram of e to the x. Now the thing that is special about e to the x is this, and this is a key thing. If you don't pick up anything else from this video, pick this bit up. If I choose any x value, doesn't matter which one it is, I'm not even going to label it with a number, any x value. And I come on up to the graph there. If I was to work out the gradient at that point for e to the x, so it would be a line kind of there, the gradient of e to the x is equal to the y value for e to the x. So the value of the graph is equal to the gradient of the graph at that particular x value. And that doesn't happen for any other graph. So whether you were looking at quadratics, cubics, square root graphs, anything else, the value of the graph and the gradient of the graph are going to be different. In this graph, when I work out the gradient at a point, it is equal to the y value or the value of the function. All right? And that's the special thing about e to the x. Okay? Hence why it's 2.718 blah 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 on forever. It's an exact number, well a never-ending exact number if you like. But that's the thing, it's only with that particular one. If you did that with 4 to the x, it wouldn't work out. Do it with 3 to the 2 to the x, won't work out. So that's the key thing, is that any x value, if we work out the gradient, it is equal to the y value of the graph. Now, that would mean, based on that, this has got to be true. If y equals e to the x, then y dash equals e to the x. Because that's what I was just saying. The value of the function is equal to the gradient of the function at any particular x value. So that's the thing. Now what I want to do, I don't want you to go, huh, okay, fair enough. I want to show you that it works. So let's get rid of this. Let's work our way through. Let's start here. If we start here, what I want to do is take the natural log. It doesn't actually have to be the natural log, but I'm going to take the natural log of both sides. Now your natural log laws, you would remember that if you've got something to a power, I can bring that out front, can't I? Okay? Something raised to a power, I can bring that out front of a logarithm. So that would now mean that we're going to have ln y equals x ln e. That makes sense? Now I'm going to isolate the x part of it. Alright? So I'm now going to write x equals, move the ln e over to this side. I'm going to get ln y over ln e. Okay? Now ln e is just a number, really. Okay? Now natural log base e. Hang on, the natural log, isn't that the log to base e? And if I've got the natural log of e, isn't that just 1? Check that up, I'm sure it's on a previous video. This is just going to be 1. Now, so therefore I get x equals ln y. Now when I take the derivative of something that is the natural log, it becomes 1 over it. Okay? You guys did that last year if you remember correctly. So therefore we get that dx dy. Notice it's dx dy, not dy dx. Because I'm starting with x in terms of y, aren't I? It's kind of the other way around. So it's logical this is the other way around. And that's going to be equal to 1 over y. Alright, well, why don't I just flip this upside down? Why don't I flip it upside down? Get it to dy dx, because that's kind of what I want, isn't it? If I flip one side, I've got to flip the other side, don't I? And do you remember way back here at the start? I said y equals e to the x. Well, that means that dy dx is equal to e to the x, which is exactly what I told you there. So if we take the derivative of e to the x, we've got to do a little bit of funky work, but it just comes back to e to the x anyway. Now, that's true, and that's fine. Be aware, be careful and be aware that we're not always going to have just x up here. Okay? We'll often have a function up there. It might be x squared, it might be x squared plus 2, it might be 3x plus 2, whatever. It could be a different function here. So I'm going to rewrite this into a slightly different format to account for not having an x up there. So let me use red here. Let's go y equals e to the f of x. I'm putting a function up top there. Now the rule for that, and we can follow this through in a similar way, and you can see it if you want to, would be y would be equal to f dash of x times e to the f of x. So you take the derivative of the power and bring it out front. Okay? And if you wanted to, you could set yourself up with a function here of maybe e to the x squared or e to the 2x plus 5 or something like that. Work it through. It'll get a little tricky on the way through, and you'll get to it showing that this actually works. Okay? So this, if you like, is our next differentiation rule when we're differentiating e to the f of x functions. Okay? Derivative of the power out front multiplied by the original. Okay? Where are we going to apply this? We're going to apply this to growth and decay type questions. This is really our next formula that we need to be aware of, and we would have touched on that briefly last year in different contexts. Essentially what this formula is saying is if a population is growing at the rate of e. Now that's actually very common. You might say, really? Well, mathematicians like to make things easier. So we use e because we've got all these rules and we understand what's going on. And then we throw a k value in there, if you like. That's our fudge factor, right? And it's not really. But what it is, it allows us to kind of modify the behaviour of e to suit our particular situation, while remaining being able to use all our mathematics around what e does and how it works. So it's kind of the best of both worlds. Now, if k is greater than 0, think this through. If this is greater than 0, and let's assume we're only working in positive time, which would make sense, then if the power here is positive, e raised to a positive power, or any number raised to a positive power, is going to give you a positive answer, isn't it? Right, think that through. Any value raised to a positive power is only going to give you a positive answer out, isn't it? So therefore, if k is greater than 0, then we're multiplying by something that is going to be bigger than 1, and something therefore that is going to give us growth. If k is less than 0, then this whole thing up here is less than 0, and anything raised to a power that is less than 0 is the same as 1 over that, isn't it? And therefore that would give you an answer between 0 and 1. And if you multiply something by a value between 0 and 1, it gets smaller, doesn't it? Okay? I want you to kind of make sure you can see that if this is greater than 0, this whole thing is positive, meaning the answer out of there must be greater than 1, which means I'm in a growth situation. If it's less than 0, then this whole thing here is between 0 and 1, and therefore then I'm in a decay situation. It's getting smaller. Right? Now, if t is equal to 0, well, that's 0, kt is 0, e raised to the power of 0 is 1, which would mean this would just fall back to P0, and P0 is our initial starting population. Okay? So if time is equal to 0, it makes sense that the value of the population is just equal to our starting population. Okay? And obviously if time is greater than 0, then we're either in growth or decay phase, depending upon the k value. Okay? This sort of idea of growth and decay really comes into its own when you talk about populations. You're talking about the growth rate of either, it could be humans, it could be animals, whatever. The growth rate or decay rate works really well here. It works really well for monetary things as well. Okay? See you, Ned.
See you, sir.
So this really comes into its own with growth decay of usually population, but can be anything. Hopefully this is helping. This I'm going to do a video on and do a couple of questions on this sort of style so you're with it. But that's the basics of it. And where does it come from? It really comes from all of this stuff here. Hope that's helped. Catch you later.